So this is a talk which is a bit different for me, and it's also a little bit different for you guys. And I wanted to share some of the things we're doing with 3D printing in pediatrics, but it goes across the department and actually across the university. There's a new effort at Children's Hospital to build a 3D printing core, and so I think you're going to see more and more of this. It does cross the boundaries between civilian life and medical life, and I think that's why it's an interesting topic. So I'm fortunate to work with Nick Thompson, who's here today. He is from the Minimally Invasive Surgery Lab and has great expertise in engineering and in 3D printing. We work together on some of these projects. And so he's going to, this is a Makerbot Replicator, which is a relatively low-cost 3D printer. So we're going to run it while I'm talking, and he's going to print a little nut and bolt, and then we'll pass it around at the end. For me, it's not until I actually saw the printer that I could wrap my brain around the concept of 3D printing. So it's pretty cool. It's pretty quiet, and you'll see what it does, and I'll talk about the process as well as we're going. It's about 2 minutes. After 2 minutes, it'll be. Thank you. All right, so briefly, here's what I'm going to do in the next 20, 30 minutes. So I'm going to give you a course historical background on printing, which, again, this is meant to touch things outside of medicine. I'm going to talk about how 3D printers work, and you're going to see that, and I'm going to talk about some of the medical applications, including what we're doing with 3D printed prosthetics. So we'll go way back. History of printing. I got a little carried away. So 200 AD in China, there was wood block printing, and that progressed over the years. So in 1440, the printing press, who knows who designed the printing press? Gutenberg. Nice. Gutenberg, exactly. In 1951, the inkjet printer. 1968, the dot matrix printer. 1969, the laser printer. And if you're like me, you're like, wow, 1980, the 3D printer was first designed. That's way sooner than I thought it was. Now, we've made great progress over the last almost 40 years in that process. So a guy named, this is interesting, a guy named Kadama, I believe from Japan, designed the rapid prototyping sequences for 3D printing. I think as Mr. Kadama was a patent attorney who didn't patent his work. Yes. Oh, yes. And so, all these years later, you can imagine the lost opportunity there. As a financial group, you guys can especially appreciate that. Charles Hull worked in a company called 3D Systems in stereolithography, and this was the first concept of layering by curing photopolymers with UV light lasers. So that's kind of really where 3D printing got going. And they use a file format called STL. I think it has nothing to do with St. Louis to my knowledge. And digital slicing and fill strategies, which are still used today. So that was the origin of this concept. In the 1990s, there was a little bit of a divergence between low-cost consumer efforts and high-end efforts, and I'll talk more about that. In 2007, a company called RepRap developed an open-source, self-replicating 3D printer. This is a guy named Dr. Bowery. And the idea was this would be the end of capitalism, because you could print your own printer and print whatever you wanted, and therefore everything would change. The irony is it led to more commercialization of the process. And in 2009, Makerbot came on the scene, and Makerbot's the name that most of us have heard of in reference to 3D printing, and that certainly is the printer, one of the printers we have in the lab, and the printer you're watching today. So, getting even more global and a little cerebral, some have called 3D printing the third industrial revolution. So let's test your knowledge. So what was the first industrial, this is back to 6th grade. What was the first industrial revolution? Anybody remember?
Steam power?
Yeah, it's a little before steam power. Steam power some would call the second, but it really goes back to textile mills in England.
Water.
And water-powered, yeah, anything that powered plants and brought people from the rural areas to the city. So it was the beginning of urbanization. Some would say the second industrial revolution was Henry Ford and kind of plants where you were on a line and you were kind of doing the same job over and over and over. That also brought people to the cities and urbanized America and other parts of the world. So the concept here is completely different. So if this works like it may eventually work, then this could spell, and granted this is a little grandiose, the end of factories and could actually promote ruralization and decentralization of manufacturing. It's a pretty amazing concept. So the concept is you can build anything, anywhere, without requiring centralized processes. So a little personal example, which is a little tangential, but my wife has a belt business, as many of you know, and so her belts are made in China, and recently she's begun experimenting and really doing development of the belts in China. They get shipped here, and then she prints the belts, or prints the designs for the belts here. And so that's a little bit of a similar example of this concept of bringing manufacturing wherever you want to bring it, rather than depending on big cities and big factories. And a lot of this is from this article in The Economist by Germany Rifkin. I thought this was interesting too, just about technologies. This is called the hype cycle by a fellow named Gartner, which talks about where things sit along this spectrum. So initially you have innovation, and then you have this concept of inflated expectations, like this is going to change the world. Then reality seeps in a little bit, and you get to the trough of disillusionment. This is really impressive. And then the slope of enlightenment. So we're probably on the slope of enlightenment with big-time 3D printing and understanding what it can really, really do for us. So what is 3D printing? It is, and I'll just read off the slide, it is successive layers of material are formed to any shape with computer control. So this it says, well, I'll go forward. It's an additive manufacturing process. And so you're instead of subtractive manufacturing, where you take a big block of steel and you cut it down to what you want, you're starting with essentially nothing and you're building something that you want. And this starts with a modeling of the desired product, so computer adaptive design, a scanner to understand what you're trying to build, and a digital camera, really the only tools you need, and then you print it. So you take this STL file, and most of what we do is open source, or much of what we do is open source, so you can download it for free from the internet. And if you have a public library that has a 3D printer, which many exist, you can print whatever you want. Now, those printers and these printers, which are relatively low cost, the cheapest printers on the market today, I think, are a couple $100. But the really impressive 3D printers are six figures and above, and the quality and the level of the micron details are very different between the two. And then what you print with depends on kind of what your desire, what you want to make. So these are thermoplastic materials, polylactides. You can also print with metals. So this is a material extrusion printer, and so basically the nozzle, which is on the tip of this device, extrudes a semi-liquid, basically heated material, and it does so in layers, again, different materials, and it comes out as a solid thin strand, which is melted, and then you can create whatever you want to do. And again, referring back to what I said before, the high-end machines can produce objects that are similar in quality to injection molding, which is what we do for high-tech things now. And there are multiple websites out there, but all of these websites will allow you to download for free this kind of shared marketplace designs for printing different things. It's pretty cool if you just go to the websites and scan what they have. Anything you can really think of, you can download and print. And it goes from the practical, like a toy boat, to the crazy, like a gun, can all be downloaded. And you probably read about some of this stuff online, because you can make 3D printed plastic guns that fire. Kind of crazy. I won't editorialize my liberal beliefs. All right, so the medical world. So in medicine, every area is using 3D printing for different things and conceptually coming at it from different angles. And so we're using it for research, education, and patient care. We use it a lot for modeling. And so, for example, if I'm doing a procedure on a humerus, and it's a complex procedure where I'm changing the shape of the humerus, then I can 3D model the humerus beforehand, and I can actually perform the surgery in my office and then replicate that in the operating room. And Larry Lanke did that, I think, well before I was familiar with this, and he had someone create 3D images of the spine in crazy scoliosis configurations, and he could both look at that himself to help himself conceptualize what he was going to do, and also share it with the families. So pretty neat.
Yeah, I know Mike Kelly's got a bunch of those models in his office.
Yeah, we could probably grab one. It's really neat stuff that you can do. It really does. Looking at a CT scan or an X-ray in 2 dimensions is helpful, but really conceptualizing in a 3D dimensional way and holding in your hands is really priceless for complex surgeries. So here's the example with the humerus. So if this is an angled humerus and trying to correct it, we can take out a slice of bone and put some metal in to fix it, but here it is done prior to the surgery with a 3D printed model. And this is relatively simplistic compared to some of the stuff that we can do. If you go back to that curve of product development, this is a little further away from reality, although there certainly is good stuff happening. This is an article from Nature in this year talking about bioprinting. And this is kind of the holy grail, right? So you can print and populate a pancreas or other organ systems if you can harvest cells, grow them in the lab, create a 3D structure to host those cells, and then implant and have the cells grow. And that's way beyond, orthopedic surgeons. Pay grade. But it's amazingly interesting, and I think it is clearly coming. I don't know how quickly it's coming, but it's clearly coming down the pathway. And you can read in the popular press things about creating a trachea, and that's been done. Creating ears has been done. So it's real. The question is, where do we get to organ printing and things that interact with the body in a different way? And then in the pediatric world, I heard more about this on Tuesday. They are using 3D printers to replicate a heart and design monitors to go on the heart, which are then implanted in vivo. So it just allows you to create the perfect design for the monitor that can then be implanted, rather than trying to figure it out as you go in the operating room. So really neat stuff there. And those, as I learned recently, those can be printed in lifelike ways. And so you can print a cardiac, I guess I would say, whole system, and a resident or fellow can then do surgery. It's not perfect, obviously, but you can operate on those 3D printed organs as a way to, again, look at what you're about to do in the operating room. So education is going to change along with the realities of medicine. So how does this interact with what we do? So traditionally, if a child is born without an upper extremity or with a partial extremity, the mantra for the last 40 years has been, when the child is old enough to sit, so 6 months of age, we fit them with the prosthetic, with the idea that if they learn to use the prosthetic early enough, then they'll use it and everyone will live happily ever after. The reality is that's not the way it works, because our prosthetics aren't that great. They're not sensate, so you're putting something on the end of a kid's arm that they can't feel with, and then you're hoping and expecting they'll just incorporate it with everyday activities. You certainly can. You can visualize yourself using the arm, so you can, instead of feeling with that extremity, you can watch yourself use a prosthetic, but it's pretty tough for a 6-month-old. And so that has come into question. And so initially, kids are given what's called passive prosthetics, and I'm not trying to give you a whole lesson on prosthetics, but they were given passive prosthetics, which essentially are just hands that are shaped like this, and they just fit on the end of the arm, and they don't do anything. They're hard plastic, and they just sit there. And they don't really look like a hand, and they sure as heck don't function like a hand, but you can use them. If you want to do bimanual activities, you can use your good hand and the prosthetic hand and kind of do some stuff, but they're not particularly functional. Maybe you can slip it on the bike handle and ride a bike, but it hasn't been great, but yet that's what we've done. And we've done that because prosthetics are crazy expensive, especially for a growing child. Kids are rough on everything, especially a prosthetic, and they're tough to use. And so a young child has trouble conceptualizing how to use a prosthetic. And so put all that together, and you hope that, well, why can't we give a child a really good prosthetic? And one of the few benefits in my mind of all the wars we've had over the last 15 years is that prosthetics have really taken off and gotten much better. And so myoelectric prosthetics have gotten really impressive. And some of the people have probably seen some, but prosthetics, myoelectric prosthetics, absolutely can open and close a hand. The forearm can rotate, the wrist can move. They're sturdy, they're durable, they're really impressive, but they're also really expensive. The government doesn't have price control for these things. They're $50,000 or more, and they often have to be replaced every 3 years. And so insurance companies sometimes will give you one prosthetic if you're born with an amputation, and that's it. And so that's why the Shriners Hospital has been central to this conversation, is they've been providing prosthetics for kids for years, although they're really low tech. So this article, which we were a part of, came out in the Journal of Bone and Joint Surgery in 2006, and it was a multi-center study which looked at how kids use prosthetics and whether they keep using prosthetics when they're given them at a really young age. and the bottom line is they don't. Many of them never use the prosthetic. Some of them use the prosthetic for limited use. But the bottom line is what we've been doing for many, many years is not the right thing for kids. And so this has kind of changed our paradigm of how we should handle children. So, fast forward a little bit, or actually go back in time a little bit to May 2011, a gentleman named Richard Van Oss in South Africa, an adult, amputated a couple of fingers and said to himself, well, this is crazy. There should be a cheap prosthetic that I can make to, extend my fingers and function like a hand. He interacted with another guy named Ivan Owen in Seattle, and the two, via the internet, came up with the concept of 3D printing. Mr. Owen was a puppeteer, and had put some of his puppeteer work on the internet, and the two of them connected, and that's how kind of prosthetic 3D printing really came of age. And the Robo Hand was launched in 2012 and became a pretty, popular press, interesting product, which has really stimulated the growth of prosthetic use, especially for upper extremities. And this is what the Robo Hand looks like, and the Robo Hand has altered, to look like different things. But the requirement for the Robo Hand is you have to have an active wrist, and so your wrist motion allows your fingers to move. And so it's a little bit backwards to what we do in real life. In real life, if you bend your wrist, your fingers automatically straighten, and if you extend your wrist, your fingers automatically flex. This prosthetic works a little bit differently. You flex the wrist, you flex the fingers. You extend the wrist, you extend the fingers. But the reality is, if you put one of these prosthetics on and you have a wrist joint, you can open and close fingers simplistically with an incredibly inexpensive device. And this is $200 to print. And like I said, this is something you do at the local library, although you do get what you pay for. They're not always very durable. As a mom was telling me today in clinic, she's had a number of 3D printed prosthetics, but they've never really been that good. And I think they kind of fall apart if they're not done in a precise fashion, which we're fortunate with Nick here to have really good stuff that provides more durability and lasts longer. So, take a look at these and compare them to the original prosthetic. Remember, that was just kind of flesh-like in color and looked like this. So this is an unbelievable conceptual shift in the world of prosthetics. So first of all, these are inexpensive. You can print them anywhere. And the philosophical shift comes from taking a kid who, most kids have some challenges with the fact that they don't have an upper extremity. In the past, we've either given them a flesh tone prosthetic that doesn't look very real, it doesn't do very much, or we've given them nothing at all and asked them to adapt. And thankfully, kids are adaptable, and once they get through 7th grade, they're usually fine. But this is a totally different concept, right? We're giving a kid this bright, shiny, talking point object, and it's a superhero in a lot of ways, and it's really been interesting to watch it work. And so you've gone from asking a kid to sort of just ignore and hide their difference to having them say, wow, this is who I am, and this is pretty cool, and other kids take notice, and other kids like it too. It's really kind of a neat thing in our world. But to make a Robo Hand, you had to have a wrist joint, and you accept that function is limited. Enable is another website which is fantastic to look up. It is a volunteer network of people all across the world who have basically signed up, and if a child or family contacts them, they'll print a 3D printed Robo Hand for this family. And so it's just a really neat site. It kind of shows the power of community involvement and the power of this free downloadable designs, and it's worth looking up. So what's our experience and how did it start? So our goals are to advance the world of 3D printed prosthetics, and there's a few people dabbling in this. There's also commercial entities dabbling in this as well, and they certainly have advantages over what we can do. And also we wanted to basically take the limited function of the Robo Hand and make it better. So it started, I don't remember how many years ago, maybe 2012, when 3 undergraduate students approached us about a senior project. So they were in biomedical engineering. They had a class where they could design whatever they wanted to design. They read about the Robo Hand, and they approached us about building this. And they had 3D printers at the BME school, and so that's what we did. We worked with them to create this product, and I'll show you some of the early stuff. So here's the earliest rendition. You can see with the hand, hopefully, it plays. Well, it's not that exciting. So it's a pretty primitive looking hand that doesn't actually do very much. It would, you use your shoulder and you control the fingers, and it showed some reason for optimism. And we published our results because, it's interesting that Enable exists, and so you can download and print a prosthetic for your neighbor. And there's some commercial work going on, but no one in the scientific community has written about this or really tried to advance the field. So there was nothing in the literature about this. So we published an article about this, and we actually have another article which is on its way, and it's generated a fair amount of conversation. And then we started working with Nick and his group, and it's kind of taken off to a whole new level. And actually, we go back. So that's Sydney, who is a patient who lost her upper extremity with a boating accident. A rope got caught around her forearm, lost her upper extremity, and has an amazing personality and resilience, and has been great as far as working with her. And she's kind of taken us to the second, I guess I'd say third generation of our work for her, and she's been on the news and done lots of cool things. So here's some of the examples. So the green is one of the robo hands, as is this, and these are the 3D printed myoelectric hands. So the concept of the myoelectric hand is you use the muscle that you have remaining in the forearm. If you fire a muscle here, it can help generate a fist, or it can help generate rotation, or it can help generate wrist motion. And so we use scanners to image the arm or the amputated site, and use those to develop the sleeve. And then I don't know if this is going to play out here. So these are all the parts that are all 3D printed and have to be assembled. And from my perspective, it's just that easy because I don't do any of it. It's funny now. And you can customize however you want. Again, we're trying to appeal to younger patients, and so making this personal is preferable in the printing process. So here's the blue arm, which Sydney wore and demonstrated. It's still a little heavy, and it's not as, there are ways that we can improve upon it, and we have. And there's some of the circuitry of the internal components. It's safe. There's no worries with it. It's essentially a 9-volt battery or less, so even if she fell in a pool wearing the prosthetic, she wouldn't get really shocked. And so it's incredibly safe. Durability is an issue. Weight is an issue, so we need to make it more durable. We need to make it lighter, and obviously we want to make it more functional. This prosthetic will never be sensate, so there'll never be feeling, although in another world, in a different area, they are making sensate prosthetics. And they actually have done some work recently where paraplegic patients can actually think about doing something, and the thought process can power their own limbs. So, everything's going to converge, I would think, with sensation, with higher level thought, and with myoelectric prosthetics to really make this come a long way. So a few more pictures. So here is this our latest? Would you say this is our latest generation? Or one back? Yeah. So this is the third generation, and now we're kind of on the fourth generation, which we fit on a patient on Wednesday night. Yeah. And it is. There's no more wires external. So there's some leads built within the prosthetic that interact with the patient's muscle, and it's really impressive. And we will show you. Is that the most recent one you have there?
That's the third generation.
Yeah. You want to show? So Nick is going to demonstrate the third generation prosthetic.
So we have cutaneous electrodes that will fit. 2 will fit on the poles of the muscle. So when I fire my bicep, and the one down here is just a negative, just so that it can read a no signal. Now, I did test this in the lab this morning, and it worked. And of course, when I'm live, it might not. But so as Dr. Goldfarb said, our current generation, we don't have these external wires. We actually have built these electrode leads into the silicone socket that fits over the patient's stump, and that's what engages into the prosthetic. So this is, like I said, a third generation as opposed to the most current. One on the elbow. So for this to work, what will happen is if I do a quick muscle contraction, the wrist should turn. Now, we've had a little stripping of the gears. This is the prototype that we keep around. So hopefully I can get that to work. I know the hand will work. And if you do a kind of a strong, maybe 1 second pulse with your muscle, it'll open and close the hand. So fingers crossed, right? So if I give a long, it should close. If I give a long one, it should open. Now, a quick one, turn the wrist. And like I said, it should have about 80 degrees of a turn, but we are wearing, the gear is actually 3D printed, so over time it runs out, but it's pretty responsive. So all 5 fingers close at once, and it's actually run off of a servo that's right here, pulling the string almost like a puppet. And we have improved on this where we have better elastic for the fingers. As you can see, the fingers kind of a little slow coming back. We're working on better finger manipulation. This prosthetic here runs off of a 9-volt battery to run the servos and a 3.7-volt lithium ion, but we've changed it to 9 volts in the new iteration of it just to make it more, I guess you could say, safe. And you don't have to bother recharging it as much. The battery drain isn't that much. We're actually testing that right now with our current patient. You should be able to get days, I mean, as long as you're not open, close, open, close. You should get a few days out of a set of batteries. One other thing to point out is when you have it in the closed position, you would, if you were going to ride your bike or sustain that position, you would probably shut the prosthetic off. It shouldn't open like that, but it did. And it would maintain that grip because you're always holding, the servo's always pulling closed. So if you shut off the power, that current stops and it'll keep it closed.
Great. Perfect. So I would just say, you know, it's exciting what's going on here at WashU and I guess everywhere. We're making great progress. I think the progress will continue, and hopefully we can continue to have a role in the 3D printed prosthetic world. We are going to interact with commercial entities and kind of see the difference in what they have and what we have, and hopefully do some testing for them. But the goal is obviously to help kids have the best possible prosthetics and the best possible function. I'll stop there. How much longer do you think this has?
It will tell us.
Did you bring any other samples?
Well, it is going a little long. It's about 55% done. But what I actually did bring was for fitting. So this is a custom socket that will fit to the patient's residual limb. We actually take that 3D scan and we print it. So this is one of our current patients' arm and stump where it ends out. And I don't have her silicone sleeve here because she has it with her prosthetic. But we go ahead and we fit that on the end of this model, and we'll 3D image this, so I can then custom fit this socket so both her limb and the sleeve will fit in. You don't get much of a. It's pretty tight. We do use Velcro just as kind of a backup. You know what will happen because kids will, you know, they're active. So we do kind of have it as a safety, but realistically it's not necessary. The suction, it's tight enough to where the suction will hold it. And that's an advantage because you don't have to wear a shoulder harness and have the thing, you know, much less cumbersome. And another advantage is if the child would happen to break this, we could print, I mean it's made up of about 56 to 60 different parts. We could print all of the parts with this. This is the actual printer we use to print these prosthetics. We could print it in less than 24 hours. So you could replace every part. So if it breaks, they could tell us, you know, what broke. We actually have the files on hand. We could make it, they could bring it in, we could repair it, and have it back to them very quick. Also with growing, as they grow out, we can scale these parts. So it's just a matter of taking another scan and scaling the parts to the patient.
So like I said, the commercial myoelectric prosthetics are between $30,000 and $70,000. And the 3D printing part of what Nick's showing you is not that expensive, but right now we need folks like Nick and other engineers that are, their time is valuable. So our estimate is around $2,000, $2,500, something like that, to design and print a myoelectric prosthetic for a child. So that cost will decrease as the time it takes to design and print the prosthetic declines as well. So just wanted to give you guys a peek into what we are doing. It's probably, if you, I don't know where everyone's rushing off to, but we'll let this finish printing, and it's amazing what it does. You'll have a nut and bolt, and the nut screws onto the bolt like perfectly. It's just pretty neat to see, and hold in hand. So it'll take another 10 minutes questions we can answer or comments?
Yeah, Chuck, so it seems like that would be natural for other types of implants. And I presume that the Qs of the world and Wrights and so forth are pursuing that or not?
Yeah, I don't know the answer to that. So one of the trends in total joint replacement is custom prosthetics. And they're certainly expensive. And I don't know that I assume they're still using the old injection molding to do the custom prosthetics. But I know that Dr. Barrick has been 3D scanning some of his patients for the custom prosthetics, but I don't think they're using 3D printing for that yet, but I don't know. But you're right, it's a no-brainer.
Is that what Parse was working on with hip joint?
I think it was. Dr. Gilak is working on hip joint cartilage replacement. I think there's some 3D components to this cartilage matrix. Yes. Yeah, you were saying Dr. Gilak may be more bioprinting, as I referred to again, which is a whole other level of sophistication. All right, thank you very much.